In this segment, we're going to discuss conservative forces, which we've actually been considering without calling them such. Because when we discuss gravity, for instance, we're dealing with a conservative force. And it all relates to what we call mechanical energy and different kind of energies transitioning between each other. Specifically, it's a force where kinetic and potential energy can interchange. And the total mechanical energy is constant. You don't lose any mechanical energy. In nature, examples of these kind of forces include gravitational force, electric force, magnetic force, and elastic forces. Of course, it turns out elastic forces are really electric/magnetic or electromagnetic, but nevertheless, we can distinguish them in a practical sense. Now, some characteristics of conservative forces that, for one thing, they're independent of the path taken. So here I have, you see my cursor, consider this a object under the influence of gravity, which perhaps is a force that acts straight down. So I can, well, let me start here. I'll start from the word path. And I can go like this, follow this around, and end up here. That's one path. And I can move this way and do all kinds of strange loop-de-loops and end up where I did before. And the work done by the force in question, namely gravity, is the same in both cases. Even though one path was quite a bit longer and more complex, the work done was the same. So that's really important. Moreover, the total work done in the round trip is, you guessed it, 0. So if I start here, and then I do this, boop, and end up back where I started, we have 0 work done. And the first point, along with that, I can take a different path. Doesn't matter what path we take. As long as I end up here, it again is 0, which is the same as the other path. So independent of path, and total work in the round trip is 0. Also, it can be expressed as a potential energy function. So if the force is conservative, it has an associated equation for the energy. The potential energy of gravity is mgy. So there's the force, mg, and there's a spatial position associated with it. US, spring potential energy, there's the equation. And it has a spatial position associated with it, namely the stretch in the spring. Now, positive work from a conservative force changes potential into kinetic. So think of gravity again. If gravity does positive work, it moves the object in the direction of the force, like that. And you realize in that positive work situation, for instance, just let an object fall. The potential energy increasingly transitions into kinetic. Negative work changes kinetic into potential. So it'd really be going the opposite way. If we take an object and it moves up, well, this is the direction it's going, but the force is still down. Those are oppositely directed, so it's negative work. And when the object moves up like that, say you toss an object upward, well, it slows down and comes to rest. The kinetic energy that it had a lot of down here becomes gravitational potential energy. So work done by a conservative force can be defined as a change in potential energy, but not regular change. It's initial minus final. So if we have an initial potential energy here, the final down here is less. So this larger value minus the smaller value is a positive number, and that is associated with the positive work done by the conservative force, gravity in this case. Hopefully that all makes sense. Now, friction, on the other hand, is negative in all directions. So if we have an object under friction and we're doing this and end up where we left off, the work done is not 0 because it was dragging against this object during the entire path. And if we take a different path, it drags against it more, so the negative work is more. So the work done in the round trip is definitely not equal to 0. And the work in the path is dependent on the path. So this is a non-conservative force, or in this case, a dissipative force, where heat is produced. Mechanical energy that you may have started, like say energy of motion, ends up, say bringing it to rest, and heat is produced in exchange for the loss of kinetic energy. So we're going to use the idea of conservative forces to analyze a problem of a spider moving around a path, and the force acting on the spider is x squared j. So we know what direction it is. It's in the y direction. We know what the size is. It's the value of x squared. All right, that's a little bit of strange force, but not too hard to visualize. So what work is done on the spider as it goes around the path? And just to clarify the path, there is path A from 0, 0 to P0, and then it goes from there up to PP, and then back to 0P, and then back to 0, 0 again. So there we just put in the actual approximate forces. Again, it's x squared j, so the direction is in the j direction, and the value is x squared. All right, so the basic equation that we have to deal with is work is integral from P1 to P2 of f dot dl. Let's look at path A. So along path A, there is the spider moving along that path, making its spider sounds. And so the force is perpendicular to dl. Well, if the force everywhere is perpendicular to the displacement, you know what that means for the dot product, don't you? That's right. F dot dl is 0. No work along path A. So let's do path B. Now we're going in the direction of a non-zero force. So F parallel to dl along the entire path. So F dot dl is x squared j, so that's the force, x squared, in the direction j, dotted with dyj, so this is the actual path direction we're taking. So j dot j is 1, so this is x squared dy, and the value of x is p, so it's p squared dy. So now let's go ahead and integrate. Work along path B is equal to the integral from 0 to p of the value of the force, p squared dy. So this is p squared y from 0 to p, which is p to the third power. So we had 0 along this path. We had p cubed along this path is the work done. And now we still have to analyze path C, which should be pretty easy if you think about it, and path D, which is also pretty easy if you think about it. So path C, the force is perpendicular to dl, so you know what that means. Work along path C is 0. And for D, if you recall, along D we're going along essentially the y-axis, where the value of x is 0, so the force is 0. Well, if there's no force, even though you're supposedly in line or parallel or even anti-parallel to the force, the motion is anti-parallel to the force, but the force is 0. It's a little weird to say that. So anyway, in any case, the work along path D is 0. So total work is adding up each of those works, work A, B, C, and D. And we just went through all those, so that's 0 plus p cubed plus 0 plus 0 equals p cubed. So that's the total work. Not equal to 0. Since it's not equal to 0, that means that F is not a conservative force. Because if it was conservative, it would add up to 0, because we ended where we began. Now this was a counterclockwise trip. What I want to do next is go around clockwise and just see if by chance anything changes. Because if the path you take doesn't alter the value, that is a characteristic of a conservative force. Now we've already determined it's not a conservative force because a round trip path does not result in 0 work. But let's try this. Let's go clockwise. Now the force is the same. It hasn't changed one bit. However, if we go clockwise, dl is reversed. All the various path elements are reversed. Well, if they're the path elements that are 0, doesn't make any difference. But what about path B? Along path B, we have f dot dl. It's x squared j dotted with dy, but you're going in the negative j direction, so it's negative j. J dot negative j is negative 1, so it's minus x squared dy, which is minus p squared dy. And if we integrate that like we did before, we get negative p cubed. So that's the total work done on the spider in traversing the path with that force, the x squared j, around the path in a clockwise direction. So that's different than p cubed. It's negative p cubed. So it does not behave like friction in this way either, because it's always, friction is always negative, and this is not negative. It's different. It's positive in one case, negative in the other. So it does, in a sense, behave like friction in the fact that as you traverse the path, you get a non-zero result. So that is like friction, but it doesn't behave like friction because of the differences in these values in traversing the path. Yes, it's non-zero, but it's different, where friction would be the same value in both directions. So this is neither a conservative force nor a dissipative force like friction. So you see that the nature of forces can be a little more complicated and a little more varied than you might have otherwise suspected. Well, let's do another example where we make that spider move around the path we had before, but this time that poor spider is going to be subjected to a different force than we had. In particular, it's going to be c plus x cubed quantity I. So the direction is going to be in the x direction everywhere, and its value is related to the value of x plus some constant. So the constant could be anything. So that means that even at x is equal to 0 along here, we have a value of force, and it's directed in the I direction. So there it is. And then over at a greater value of x, we have a greater value of force for obvious reasons. So can't really show the whole field of forces. It's kind of like a vector field. At any value, any point in space, that vector points in the I direction, and its value is increasingly going up as we progress in the x direction. So basic idea, work is integral from p1 to p2 of f dot dl. And let's do path A. There it is, spider going along A. Now, we know that in that direction there is a force along there, right? It wasn't 0. F dot dl is c plus x cubed I. And you're dotting that with dl, which is dx, I direction. Of course, I dot I is 1. So this is c plus x cubed dx. So that's the value of f dot dl. So the work along that path, let's integrate f dot dl. We integrate along that path, 0 to p, the value of the force, which is c plus x cubed, dl becomes dx, and of course this is a function of x. So therefore, we got cx plus x to the fourth over 4 from 0 to p. Sticking p in there gives us cp plus p to the fourth over 4. Sticking 0 in for x gives us nothing. So that's the value of work along path A. Path B, well, again, the force is perpendicular to the path. Therefore, work done along path B is 0. And now let's do C and D. Let's consider path C, f dot dl. So you're going on the top of that path toward the left, and there's the force, direction I. So f dot dl dot dxi. So that's c plus x to the third dx. I dot I is 1. So the work along C, in this case, we're really integrating, not from 0 to p, but from p to 0 in the x direction. So that gives us cx plus x to the fourth over 4 as before, but from 0 to p, we get negatives. Negative cp minus p to the fourth over 4. And then path D, coming down to along the left edge like this. Well, we're going perpendicular to the forces, and therefore no work along that path. So work total, A, B, C, and D. We have Cp plus p to the fourth over 4 minus Cp minus p to the fourth over 4 equals 0. This is going counterclockwise. If we go clockwise, it just changes the sign because the integration path has been reversed. So total work then is minus Cp minus p to the fourth over 4 plus Cp plus p to the fourth over 4. 0. So it's conservative force because as we completed the path, round trip, you end up with 0, and it's path independent as well. So there is a conservative force. Oh, that's kind of disturbing. I don't know why I felt compelled to have that come on the screen. Well, if you've survived that spider incident, then let's bolster the idea that this is a conservative force by showing that we can represent this as a potential energy function. Work done by a conservative force is minus delta U, and therefore the delta U is equal to minus work done by the conservative force. Well, what is delta U? Isn't it just final minus initial? Well, yes, it is. So final potential energy minus initial is minus work done by a conservative force, which is integral of F dot dl from P1 to P2. It's spatially related. So this is minus P1 to P2, the integral, C plus x to the third dx. So there we go. That's U minus U0. So solving, we get minus Cx plus x to the fourth over 4 from P1 to P2. Now along the x-axis, you can consider where we start. 0 is at the 0 point of x, so U0 is 0. There is no potential energy at the beginning at x is equal to 0 because there's no spatial extent through which that force can act because it's at the reference point, just like 0 gravitational potential energy at our reference elevation level, perhaps on the ground. Same idea. So therefore, U is equal to minus Cx minus x to the fourth over 4. That is the potential energy. Considering that P1 and P2, well, P1 is just 0. P2 is the value of x. So there it is. So now we've seen that this potential energy can be written as a function of x, which is one of the characteristics of a conservative force. Only conservative forces can be expressed in that way, in terms of potential energy function. If not, the alternative is that there is a change in the internal energy with the object equal to minus work other. If we think of friction, friction is negative, and negative, negative, I should say friction, work done by friction is negative. So if you take a negative, negative, you have a positive. And so you change the internal energy of the object through friction by causing heat. The average kinetic energy of the atoms making up the object increases. It changes the internal energy of the object. So, general conservation of energy, change in the kinetic energy plus change in the potential energy of whatever version it is, plus change in the internal energy, which accounts for the work other, that's equal to 0. And I hope that makes a little bit of sense.